For the remainder of today, we're going to look at the behavior of the models that we've looked at the last time and today on a number of controlled syntactic tests. These will include the Guler-Dava and Josefovitz models of last time, which are sequence-based LSTM models. They're trained on relatively large amounts of data. Guler-Dava et al. Is trained on 90 million words. That's sort of childhood's worth of data of Wikipedia text. And Josefovitz et al. On an order of magnitude more than that of web text. This is about a human lifetime's worth of data. And the recurrent neural network grammar model that we just described we'll also look at. This is trained on only 1 million words of data. It's a very small data set, but it's syntactically annotated. And so human annotated data sets are very small. And so it's only 1 million words, a very small amount of text, really in the context of sort of an appreciable amount of experience for human life. And then as a control for the hierarchical structure of the recurrent neural network grammar, we'll also have just an ordinary LSTM model trained on that same data set. And of course, the LSTM models don't have an explicit syntactic state representation, but we saw last time they can actually learn a fair amount of things about syntax anyway, and we'll compare that with the model that actually does have explicit syntax. So the first test that we'll do is an extremely simple test of one characteristic of syntactic hierarchy. Once again, the signifying characteristic of syntactic hierarchy is generally a dependence between elements that may be linearly distant from each other. And hopefully the following template will illustrate that quite clearly. So let's look at a simple pattern. This is a sentence: the doctor studied the textbook. You probably think that's a perfectly ordinary sentence, nothing wrong with it. I'll give it a green check. Compare that to the sentence, as the doctor studied the textbook, period. This probably feels like the sentence fell off a cliff. It just didn't end. That intuition is, I think, quite widely shared. It's very strong, and so I'll give that a red X. That's a bad sentence. Now let's look at a couple of other versions. Let's replace the period with another clause. The doctor studied the textbook, comma, the nurse walked into the office. This you might find is, it's not totally awful, but it's a little weird. It's a little weird for two clauses to be juxtaposed like this with each other with only just a comma. So I'll give that a little bit of a yellow question mark. Not as bad as the second sentence, but not as good as the first. And now, as I went from the first to the second sentence, I added an as. Let me go from this third to the fourth sentence and add an as again. Now I have, as the doctor studied the textbook, comma, the nurse walked into the office. And you probably feel once again that this is a perfectly fine sentence. And now notice that this is what we call an interactive pattern. So there's a contingency between the presence or absence of as and the presence or absence of a second clause after the first clause, okay? And that contingency, I want you to actually go back and think about subject-verb agreement, which we looked at the last time. With subject-verb agreement, there was also a contingency between two things that had to be, that had to be matched, but could be linearly distant from each other. In the subject-verb agreement case, it was the contingency between the form of a particular noun in the head noun of the subject and the form of the finite verb in the sentence. Those two had to match. So it was a contingency between the forms of two specific words. Here we have another contingency, but it's not a contingency between the forms of two particular words. It's a contingency between the presence or absence of a particular word early in the sentence, here the word as, and the presence or absence not of a particular word, but of an entire phrase. And the phrase could take any of an infinite number of forms. What is that phrase? The phrase is the main clause of the subject, the main clause of the sentence. So this is a contingency which also, like subject-verb agreement, reflects syntactic hierarchy, but it's one that's a little more abstract and a little different from the subject-verb agreement case. Now, how do we test whether a model has acquired knowledge of that contingency? So what we're going to do is we're going to do a test conditioning on the context, asking what predictions does the model make about what's going to come next. That is, are its expectations about the upcoming syntax guided in a way that's human-like? So we'll divide each of these sentences into the context and the continuation. So for the first sentence, the context would be everything before the end of the sentence, the period, and the continuation is just the period and then the end of sentence marker. So that's a complex context in the continuation, or actually since it's the end of the sentence, it's the completion. And we're going to be interested in the surprisal or negative log probability of the completion given the context. Okay, so I'll circle the continuation here and then just omit the context bar continuation bit. So these are the 4 continuations that we're interested in. Okay, and now remember, surprisal is high when something is unexpected. And let's call the first examples here, we'll call them the no matrix variants. And I'm going to call these the no matrix variants because there is no matrix clause or main clause after the first clause. And the bottom 2 are matrix variants. That is, after the first clause, there is a subsequent matrix clause. And the contingency should be reflected in modulating of the probabilities of those completions. But now notice that unlike in the subject-verb agreement case, where we could take the 2 different kinds of continuations and just ask which one, does the right context assign a higher probability to the continuation of no clause or yes clause, that would be very difficult to pull off because the continuation in the no subsequent clause is just a very little bit of linguistic material. It's just a period in the end of the sentence. Whereas in the matrix clause, there's a whole bunch of material. So it's going to be hard to compare models fairly on dramatically different quantities of material like that. Rather, we're going to do something a little different. We're going to ask, holding the continuation or the completion constant, does changing the context do the same thing, do the right thing, do a human-like thing to that completion probability? And so what does that mean? So if we look within the no matrix variance, we modulate whether or not the word as appears in the context at the beginning, does that affect the surprisal in the right way? So for example, if I mark this as sentence A and sentence B, and the surprisal of, we'll call this surprisal of, the surprisal of sentence X, where X is either A or B, and then I look at the surprisal of B minus the surprisal of A, I should find that this is a positive value because the human-like model should be more surprised for the sentence to suddenly end after as the doctor studied the textbook than it would be for the sentence to suddenly end after the doctor studied the textbook. So a human-like model will have a positive surprisal differential for B minus A. In contrast, for the matrix variance, the surprisal differential should go in the opposite way. So if I call this C and D, then what I should have is that the surprisal of D minus C is negative because C is more surprising than D. And so now we're going to look at the behavior of these models. We'll start with the large neural network language models, and to orient you to these graphs, I'm going to plot that surprisal differential on the y-axis of the form that I just showed you on the previous slide. And then I have the no matrix and matrix variance. The no matrix variance will be on the left, and so what I'm going to show you is a bar. And if the model is totally insensitive to whether or not the word as was there, for the particular case, the particular continuation, then the bar will be at 0 because changing the context doesn't have any effect. So let's actually see how these 2 models behave. Well, this is interesting. So remember that this is the 800 million word model. It's a huge model, and this is the 90 million word model. So actually, the human-like behavior, once again, should be that the no matrix variance should have a positive surprisal differential. The matrix variance should have a negative surprisal differential. And what we actually see is that this 90 million word model of Goulart-Dava et al. Has a human-like processing behavior. It actually is more surprised for the sentence to end after as without a matrix clause, and more surprised for there not to be a sentence more surprised for there to be an extra sentence if there was no as. Okay, and so these are both human-like processing patterns here. So up for the red and down for the blue. The even larger model actually fails to show sensitivity to the presence or absence of as when the sentence ends suddenly. So even though this is a model that has remarkably good perplexity and is trained on an enormous amount of text, it actually has failed to learn this very basic contingency. On the other hand, it does succeed in increasing its expectation for sentence-like continuations for the matrix continuation. So it's got the blue bar in the right direction, but it doesn't have the red bar in the right direction. Now let's look not only at these models, but at the smaller model. So this was the no matrix penalty. This was the matrix licensing effect. The top 2 facets of this graph here are the same ones that you saw just a moment ago. And now the small matrix, the small data sets with only 1 million words of training are on the bottom. So if we take a sequence model, it still actually learns a little bit of that contingency, and but fails to learn the sudden sentence end surprisal effect. But now look at what happens when you actually have an explicit grammatical representation in the RNNG, the recurrent neural network grammar. Suddenly, you have actually a very clear pattern, both of surprise after the sudden end of a sentence that began with as without a matrix clause. So that's a very positive big surprisal effect here. And then down here, we have a big surprisal effect here for continuing with a second matrix clause if you didn't have an initial subordinator. And so actually, I want to also draw your attention to the fact that if you remember back, that the most anomalous of those sentences, of those four that I gave you, was as the doctor studied the textbook, period. That was a big surprise effect that you probably experienced when you ended the sentence when we ended the sentence with a subordinator and with no matrix clause. That actually should be a big surprisal differential for the red bars, because that was the no matrix variant. But actually, the only model that shows a really big effect in terms of the magnitude of the surprisal effect is the recurrent neural network grammar model. Even the model that the other LSTM model that shows that effect has a smaller surprisal effect of that type for that condition than for the matrix continuation surprisal effect here. So actually, in a very meaningful way, I think we can say that the neural network model that is on an explicit symbolic grammatical representation gives the most human-like processing behavior for this extremely simple case of a subordination. So in summary, we found that all the models that we looked at learned something about the contingency between an initial subordinator and the need for a second clause. But the explicit representation of grammatical structure substantially sharpened the learning from that contingency.